Good day, everybody. Can you hear me and can you see my screen? I'm sharing my desktop.
Yes, sir.
All right, thank you very much. Let's take a moment just to scan our attendance over here, and then we will start with our class today. Okay, how's everyone doing today? How's everyone doing throughout the last week? Good.
Okay, sir.
So I would like to know, just before we start the class, I would like to know also if there is any one of you who would like to feedback to me. How do you feel about our quizzes? How do you feel about our classes so far? Are you guys keeping up, or are you guys struggling? I'd like to know that. Anyone?
I have a problem with the C C D B C D. Is it that last question for the last quiz? I'm still a bit hazy on that one. I just watched the video. I tried it myself, but I think I got it wrong or I didn't finish properly. So if you can touch a bit on that, that would be awesome.
Okay. All right. Thank you for bringing that up because I wasn't planning to touch on that one. Okay, anyone else having the same issue? Let me just bring that up a little bit. Anyone else has anything to add to that? Um,
I just joined the class. Have you released the QR code?
Sorry, I didn't get you.
No, I just joined in. Have you released the QR code?
Yeah, I will do so in a moment.
Okay.
Yeah. Okay, my background is a little bit noisy, so I couldn't hear you guys very well actually. Do you guys hear any background noise coming from my side?
Yes, a bit, sir.
Yeah, because there's a renovation going on in my neighbor's, like I think next to my unit or something. So is it too distracting or not? Like, I'm not sure how loud or how clear it is.
It's not so loud, so it's still okay, sir.
Okay, all right. So hopefully the recording is fine. Okay, so let me share my screen again and wait. This is super annoying from my side. Like I couldn't really focus on this. Okay. Let me share my screen again. Okay, just as a recap. Okay, you guys seeing my screen, right? Okay.
Yes, sir.
Yes, sir.
All right.
Yes, sir.
Okay, so some of you have just now voiced out on the last thing that I didn't taught in the class. Actually, I did that intentionally because first, what I want you to learn from my class, and I hope you learn this early on throughout the semester. In my class, I don't want you to learn what I say. Of course, like whatever I teach you in class, take it. But what is even more valuable than that is to learn how to learn. Okay, you get, so what does that mean to learn how to learn? So learning is not just I mean, for you, I really hope that you can take this in. Like in this class, I really hope that the thing that you learn is not only limited to what I say in the class. Okay, so that's why in this semester I'm changing the approach a little bit. So I will teach you around 90%, 90% of the topic usually around that. And the other 10% is what I want you to go out and explore and learn for yourself. So by doing this, I really hope that you guys can embark on a journey to do self-learning. Okay, of course, some of you might think that, oh, okay, that self-learning is like is like, am I just shrugging off my responsibility as a teacher in the class? No, I'm not. If you want me to teach that, yes, I can still do so. I can still teach that in the class. But I think there is only a limit to what you can learn by me talking like this. Learning is not like a one-way street. So I really hope that you can learn outside of the class by doing yourself. And certain things, I really hope that you can learn by exploring. Because let's face it, like knowledge is everywhere. Okay, knowledge is everywhere. All you got to do is to start getting your hands dirty. Start by watching these videos and just start at this point. I really hope that you can, if you can apply this concept to every online class. I don't think you ever need to attend any online class, to be honest with you. Right? Of course, like we are under like university policy, and the policy says you have to attend class. But I'm telling you the reality over here. Everything is online nowadays. All you need to do is just get your hands dirty and start learning it yourself, not learning by listening just to me talking. Okay, so I really hope that this will be a little bit of a reminder to everyone. Okay, so let's talk about what we did in the last class. So actually, with the last class, we have finished covering number systems and operations. So the only thing that I didn't teach you in the class was this element, which is codes. And one of the codes that that was covered in this course is known as BCD code. So I believe if you just go onto Google, go onto YouTube, there's a lot of videos out there that is like 100 times better than how I can ever explain this topic. Okay, so let's face it, I accept this reality. So there are so many good teachers out there releasing their videos for free. So what I want you to do is to also expose yourself to good explanation by good teachers. So that's why I encourage you guys to watch this video, and that's why I really post this video after every class, and I really hope that you guys watch this video actually. All right. Okay. So since some of you have said that you have trouble understanding BCD code, okay, I will briefly use this time to cover what is BCD code, and then we'll proceed on with today's class. Okay. So BCD code stands for binary coded decimal. So it's very, very simple actually. So if you look at numbers, so computers can also encode numbers in this BCD code. Okay, this is one format of computer storing numbers. So the reason why it is used is because it's easier for humans to read. Okay, so the idea over here is that each decimal digit is represented by 4 binary digits. So let me give you an example over here. So in decimal number, you have digit 0 to 9, right? So each digit 0 to 9 can be also represented by this number. Okay, like for example, 0 can be rewritten in BCD form to be 0, 0, 0, 0. Okay, if I have number 3 in decimal, I say that, okay, now change this into BCD form. So what you can do is that you convert this into, it's actually just a binary conversion. So 3 equivalent in BCD or in binary is actually 0, 0, 1, 1. Okay, same thing over here. Every one of this is the same. All right, and what makes it different from a usual binary conversion is that this BCD code only has got 4 binary digit. Okay, only 4 binary digit. Right. And the other thing to note is that from 1010 to 1111 is invalid in BCD. Okay, if you take a look over here, right? So we start from 0000, which is here, and then we go up to 1111. So what about the rest? There is more digits until we reach 1111, correct? There's more digits, there's more numbers over here. So 1001, after that will be 1010, and after that will be 1011, and so on until you reach 1011. So all these numbers in BCD, they are known as they are not valid because there is no equivalent number for that in decimal. Okay, so let's just look at what it means. Okay. So the key point over here is one decimal digit is represented by 4 binary digit. Okay, so this is one example for it. So if you have like the number like this, 85, So what you can do is actually break this down into 2 decimal digits over here. And you know that in BCD, each decimal digit is represented by 4 binary digit. So what you do is you look up 5. What is 5? Equivalent of 5 in binary. And this forms this portion. And 8 forms this portion. Okay, this one example. This is another example. Same thing again. Okay, and take note over here that the base over here. Okay, so sometimes this is how we write it. To just take note that this is in the BCD format. It's not in a binary, or it's not in other kinds of number format. Okay, so it's not this. It's not 2. Even though it looks like binary, but if you write this over here, BCD, then we know that this number is actually in BCD format. Okay, so same thing over here, 24. You separate with 4 digits and 4 digits. Okay, so the thing about this is that with BCD, we can also do addition. We can also do subtraction, actually. So what we want to do is this has got some exception. Remember just now I said that the number between 1010 up to 1111 is not a valid value in BCD. Okay, not valid. Okay, so in any case, when your addition is more than 9, you need to add 6 to the sum. So why is it more than 9? Remember, the last digit that is valid in BCD is actually the decimal value of 9. Okay, so after 9 up to this value, so after this 1001 to 15, so it's not a valid number. Okay, so how many values exactly in between this? It's actually 6 values. Okay, so you can count. Let me just do. So there's like 6 invalid values over here. Okay, between 1010 and 1011. So you can do just 1 1 1 1 0 1101 1110 and wait, did I miss any number? 1 1 1 2 3 4 5 6. Yeah, 1 2 3 4 5 6. Yeah. So if you count the number of invalid digits here, there's 1, there's 2, there's 3, there's 4, there's 5, and there's 6 invalid digits. So that's why in BCD, when you add a number and the number goes beyond 9, you need to add 6 to that, because there are 6 invalid digits over here. Okay, the other thing is that if there is a carry, you need to add 6 to the sum. Okay, so let me just go through an example over here. So we can do this addition, and if you do this addition, we know that this number 8 in decimal, right? So you can do the same in BCD. If you do BCD addition, it's the same like binary addition. All you got to do is 0, 1 plus 1 is that, and 1 plus 1 is that. Okay, so what is this number in binary? Sorry, what is this number in decimal? This is also equivalent to 8 in decimal, right? Which is the number that you expect to get. If you do 6 plus 2, you know that you get 8. Okay, this is how we verify this answer. Okay, however, there are situations like this. 7 plus 3. Okay, let's take a look at that. So this is how you write 7, and this is how you write 3. And if you do this addition, let's do it real quick. 111 is 11. 111 is 10. Okay, so 10. Okay, so this would be okay. Let me write the base number. Okay, so we know that we should get a 10 over here, right? We know this. However, this 1010 is not a value that is valid in BCD. Okay, remember I showed you in the previous slide. Go back here. These are all the values that are valid in a BCD, starting from 0000 up to 1001. 1010 is not a valid number, okay, in BCD. So because 1010 is not in this row at all, you see. So in this case, what we need to do? So in this case, what we need to do is we need to add 6 to the sum. Okay, let's just go back here. Okay, this was what we did just now. So this number, unfortunately, is not a valid number, right? Not valid. So to make it a valid number in BCD, what we do is we add 6 to that. Add 6. So what is 6? 6 is 1. 6 is 0110. Okay, binary, remember? You add 6 to that. And what do you get? So I already have that. So you add that, and the answer would be this. Now, this is a valid value in BCD. Okay, 0000 is valid value in BCD, and 1 is also a valid value in BCD. Okay, and if you take this number, you will see that if you group this like this 4 is a 0, and this 4 over here is a 1. Okay, which is what we expect to get, 10. Okay, clear on that? So this is the first case when the number, when the sum is more than 9, you want to add 6 to that. Okay, that is the rule that we have had, that I've told you guys just now. Oops. Okay, now let's take a look at the other one. So okay, so this is the first rule, right? If the sum is more than 9, you want to add 6 to the sum. And the other rule is that if there is a final carry, you want to add 6 to the sum. Okay, let's take a look at this rule, this second rule. Okay, so let's take a look at this. Say you have this big number over here, and let's take a look at how we do this addition. Okay, so first number 490. So if you take a look at this, this is 4, this is 9, and this is 0. Okay, and 497, what do you have? 497. Okay, same thing. This is 4, this is 9, and this is 7. Okay, now let's take a look at how we do the addition. So the addition will be just like any other addition. Let's take a. Okay, so if you do this addition, let's just do this. 1 over here is 1, O plus 1, 1, O. So 1 plus 1 is 1. O, 1 on 1 is O, 1. Okay, so you have 1 over here, O, 1. Okay, so this is the answer that you get. So the second rule is over here. This thing has final carry, so we need to add 6 to the sum. So what do we mean by has final carry? Okay, so final carry means if there is a carry that brings over to the next group. Okay, so in this addition, there is a carry that brings over. So for that, we need to add 6 on this group. Okay, so if you do that addition, then this is what you will get as your answer. Okay, so if you look at this, 1 over 1 is 9. 1 is 1 is 8, and this is 7, I think. Yeah. Yeah. Okay. So again, I've uploaded, I've attached this video over here. This video is meant to give you a better understanding on what's going on. Okay. All right. So that is it about BCD addition. Any question? Do you have? If anyone has any question?
I have a question for when after you add the 6 and one of the four bits at the bottom is like a double digit number, like 13 more than 9, I mean.
So yeah, So have you watched these two videos?
I watched it, but the way he did it, his double digit number was at the back, and when I was doing it, my double digit number was in the front. So that's my main confusion actually.
The front, you mean here?
No, that's the back.
Okay,
The
you mean here?
left side. Yeah.
Okay, I haven't come across that yet so far. Like if you're willing, then we can discuss after the class maybe, if it's just specifically to your case, because
So
everyone.
Yeah, sure.
Yeah.
No
I also
problem.
face the same problem, sir.
Okay. Right. Please stay back after the class so that we can have a look at the question itself. Okay. Any other issue with the quiz? Okay, if there is no issue, then yeah, to those who have any problem, like please do stay back later on, and let's see what's the problem that you are facing in this BCD. Okay, all right. Okay, so for today we will have to cover our class content. Make sure we are on schedule. So let me just open this class topic 3. Okay, so this is the QR code to those who came in late, and then I'll display this QR code again at the end of today's class. All right, so let's dive into this topic so that we can learn more about logic gates. So in this topic, I'm sharing my screen, yes. So in this topic, we are going to dive deeper into the course, and in this course, what we are learning about is actually gates. This topic will be a fundamental topic for everything that will come up in the course. Okay, and a fundamental understanding of logic gates is something that we will learn in this topic. So let's take a look at what is it exactly logic gates. And to some of you, you might have learned this in your previous classes or in your previous course. And if you have not learned about this, don't worry, it is still a very straightforward topic. And I foresee that in today's class we'll be able to finish this topic, right? Okay, so let's first talk about Boolean first. So Boolean is actually a dude's name. Okay, dude's name. His name was George Boolean. Okay, so he is like the entire. He's like the founding father of this idea that computers can store value in these two states. Okay, it is either a 0 or it is either a 1. Okay, so these are known as Boolean values. Okay, so we'll talk a lot about Boolean values over here. And in Boolean values, things are very straightforward. So there are only two possible values, and it is actually 1 or 0. Okay, in digital logics, that is what you will see. It's one of the two. It's either yes or no, true or false, 1 or 0. Okay, now you can think about it. Like there are only two possibilities. There are no value in between that. Okay, that is Boolean. Okay, so let's also talk about logic gate. In any logic gate, we also have two components. Okay, so two components are the input and the output. So input is whatever you feed into the logic gate. Okay, this logic gate over here can be one gate, it can be many gates. Okay, many gates as in a combination of a few gates. Right, so the input, usually you would see this arrow going in, then you know it's the input, and arrow going out of the block, that is an output. Okay, right, so straightforward so far. So how do we describe how gates work? So let's say I give you a logic gate like this. Okay, how do you describe how the operation of this gate? Okay, so this is an AND gate, by the way. We'll take a look at it after this. So, but how do we describe this operation? So if someone asks you, how do you describe the operation of this gate? do we start drawing out and then like start telling them, oh, if this is 1, then this becomes 1? No, right? That is a very long way of explaining how the logic gate works. Okay, if you have like 1,000 gates, how do you describe how this 1,000 gate works? So there's 3 ways for us to describe how this thing works. Okay, and these 3 are, it can be applied to any number of gates. Okay, if you have 10 gates, 100 gates, and 1,000 gates, like these 3 things is going to kind of summarize things, how the system works. Okay, so the first one is truth table. So the truth table is a table that does what? That tells the truth. Okay, no, a table that shows you the relationship of the inputs and the outputs. Okay, so a truth table will have these 2 elements. You would see later on, we'll draw a lot of truth table in this course. But for now, know that a truth table will contain all the inputs and all the outputs that is associated with this gate or a combination of gate. That is one way of describing how a system works, how logic gate system works. Okay. The second way is to describe that using something we call a timing diagram. So a timing diagram is a graph, okay? And it's a graph and it shows you certain waveform, a waveform of the logic values. All right, and the third way is Boolean expression, okay? So this Boolean expression is a type of mathematical expression that is used to define the operation, okay? We'll take a look into detail, in detail about how we go about producing these 3 things. Okay, let's take a look at this. So these are the 3 logic gates that I want to introduce to you guys today, and these are known as basic logic gates. So we have also non-basic logic gates, and we'll also talk about that later. So the 3 most basic logic gates, they are NOT gate, AND gate, and OR gate. So why do I say that this is a basic logic gate? Because this basic logic gate is like the basic unit. Like you cannot break this into smaller units anymore. These are like the basic Lego blocks to build many other gates. Okay, so all other gates are basically just a combination of between these 3. Okay, so for example, you can combine NOT gate and OR gate and you form an advanced gate. You can combine AND gate and OR gate, you can form another gate. Okay, but these 3, they are the basic building blocks of gates. Okay, so you cannot break these basic blocks into smaller units anymore. So that's why they are known as basic. Okay, so we are going to look at these 3 basic logic gates, and we are going to try to produce the 3 things: the truth table, the timing diagram, as well as the Boolean expression. Let's take a look at how we do that. Let's start with the simplest of all. This is the NOT gate, right? So this is how we draw a NOT gate, right? So there's a triangle and then there's a bubble at the end of the triangle. Okay, so for a NOT gate, the input is usually on the left and the output is usually on the right. Okay, and the input usually we label is as A or X or Y. Okay, the label doesn't matter. Okay, that it can be any other letters, any other alphabets over here. Okay, of course. Can I draw this gate like can I draw this like this? Yes, of course. You can always draw these gates however you like it. Okay, as long as there is a triangle and there is a bubble in front of a triangle, then you know that it's a NOT gate. Okay, but the most usual way to draw it is like this, because it's easy to see. On the left is the input, on the right is the output. Okay, but don't be surprised if you see something like this or something like this. Okay, it's still a NOT gate. So if you have this kind of drawing, it means that the input is here and the output is here. Okay, so not a big deal. So that is the symbol, that's the input, and that is the output. All right, let's take a look at the Boolean expression. So the Boolean expression is an equation that describes how is this related to this. How is X related to the input A? So how do you calculate the value of x if you have the input a? Okay, so this expression over here is very simple. So what this expression means is that if you have a value of a, you can calculate x by taking the a and then you put a bar on top of it. So what that means, if you have a bar on top of a, it means that you invert the value of a. Okay, so now we have two examples over here, right? We have two possible values of input. So the input a over here can be 0 or it can be a 1. Okay, digital logic, remember, it's either 0 or 1. There's no other possible value in digital logic. So let's talk about this. So if the input is 0, what is the output like? What is the output? So if you want to know the output, first option, you can take a look at the Boolean expression. That is how the Boolean expression says the output is the inversion of the input. Okay, now in this case, we have the input to be 0. Now the output in this case will be the inversion of 0, which is 1. Okay, on the other hand, if you have input to be 1, then the output will be the inversion of 1, which is 0. So that is how you interpret this Boolean expression. Okay, that is one way of describing how this gate works. Okay, so that was what I was saying. This is the inverted value. Okay, right. So now let's talk about another thing. So we have NOT gate, and now we want to see what is the truth table of a NOT gate. So the truth table of NOT gate is very simple. It looks like this. So as I said earlier, a truth table, you must have input and you must have the output. Okay, a truth table that is not complete with the input and output is not correct. So a truth table must have all possible values of input and all possible values of output. Okay, so let's take a look at this. So what are all possible values of A? As I said just now, it can be either 0 or 1. These are all possible values for A. Okay, for output as well, it can be either 0 or 1. So this table will need to tell you if the input is 0, what is the corresponding output? If the input is 1, what is the corresponding output? Okay, so as we have seen just now, this gate just does the inversion. It just inverts the value, and this should reflect at the output. Okay, right. So that is the truth table. So we now have Boolean expression, and now we have the truth table. Now let's take a look at the third one, the timing diagram. So how do you write, or how do you draw a timing diagram? So a timing diagram will look like this. Okay, so you have you have the input and you have the output together on the same axis. Okay, and you have an axis over here that says time, and over here is the value. So what is it? What is it that we are drawing over here? So this value, well, actually you can separate it like that if you want. Okay, if it helps you see clearer. So let's take a look at the bottom portion over here. Sorry, let's take a look at the input portion over here. A. Okay, the input is A, right? So if the A is 0, okay, the time when A is 0, what is the output? The output will be 1, okay, at the same time. So this one denotes like time, right? So that's why we have a vertical dotted lines over here. So all of a sudden, if A changes value from 0 and it changes 1, at that instant of time, the value of X will also change to be 0. Okay, so and then 0, and then this becomes 1. So that is how we draw a timing diagram. Okay, is this clear? Straightforward, and a timing diagram should also have all combinations of inputs. Okay, so for here, for the NOT gate, all combinations is 0 or 1. Okay, so over here we have A equals to 0, which is this portion, and A equals to 1, which is this portion. Okay, so this two portion needs to be in the timing diagram. Okay, and after this is just a repetition. So we'll stop drawing at this point. Okay. All right, so we've seen three things right now. We've seen Boolean expression, we've seen timing diagram, and we've also seen truth table. Now let's take a look at how these three things will look at for other gates. Let's take a look at this. Okay, yeah, before that, let's take a look at the example or application of a NOT gate. Okay, so let's say, suppose you have a flood warning system, and this flood warning system has a value of 0 or 1 to tell you about the water level. Okay, so if the value is 0, let's say this is a sensor value. Okay, sensor value of a flood warning system. So this sensor value can have two values if this is a digital sensor. Okay, a digital sensor can have two values over here, so 0 or 1. So we can fix in the system that says if the sensor value is 0, then that could indicate a high water level, and if the sensor value is 1, it could indicate a normal water level. Okay, so what we want to do in a system like this is that if the water level is high, which is here, and we want to trigger an output of 1, and this output of 1 is connected to a warning system. Okay, so if this input is 1, water level normal, and then this AND gate will just invert, and this warning system will not get triggered because it gets a value of 0. Okay, this is an example application, and we'll take a look at how it is done in real life situation, like at the end of this class. So we'll have like a mini project. All right, let's take a look at AND gate next. So AND gate, similarly, we have the three components that we talk about, and we have this as well, symbols, and we have the input, and we have the output. All right, so the input, as usual, I like to draw it like this on the left so that it's easier to see. And the difference we see from the AND gate is that for the NOT gate is that the input has got multiple inputs. Okay, so we label it as A and B, but really you can use any other letter if you wish. And the output, I'm going to stick to the same letter of X. Let's take a look at the first thing over here. That is the Boolean expression. Okay, Boolean expression. So a Boolean expression should describe what is the value of X if you know these two input values. So the Boolean expression for AND gate is simple. So the Boolean expression for AND gate is this, and this over here, it means multiplication. Okay, so you take A and you multiply it with B. Okay, so you take a value. If A is 0 and B is 0, so the output will be 0 because 0 multiplied by 0 is 0. Okay, same thing you can do for other combinations as well. Okay, so let's take a look at okay, so this is how I like to remember the AND gate. The AND gate is so simple. It only gives you a value high output when all inputs are high. So what do I mean by high? High means logic 1. Okay, high means logic 1, low means logic 0. So the input will only be 1 if both, the output will only be 1 if both of the inputs, they are 1. Okay, that's how I like to remember this. All other combinations of input, 0, 0, or 1, 0, or 1, 0, they all will give you an output of 0. Okay, the only time when it is 1 is here. Okay, that is how I remember this AND gate. All right. Okay, let's take a look at how the truth table will look like. So for this AND gate, notice that we have 2 inputs and 1 output. Previously in the NOT gate, we have 1 input and 1 output. So for the truth table, in this case, we need to have all the inputs over here. And if you have more than 1 output, you need to make sure the output is over here too. But over here, we only have 1 output, so that's all we got. Okay, so let's take a look at input A and B and what are the possible combinations of the input. So A and B, A has got 2 choices of value. B also has got 2 choices of value. Can be low or it can be high. Can be 0, can be 1. Okay, same thing. Now, what we want to have in the truth table is it's all possible combination. We can have A0, B0, that is one possibility, and we have A0, B1, that's another possibility, and so on. 1, 0, another possibility, and the final possibility is 1, 1. Okay, that is how we fill in this part. Now, for the output, how do we fill in the output? So the output, for the NOT gate just now, we see that the output is just an inversion of the input. Simple enough that you don't need to refer to the formula. Okay, but for AND gate, the output, you know that it's still very simple. It's just multiplying, it's just taking A and B and multiplying it. So if you take over here for the first row, all you got to do is take this value and you multiply it, then you get the output 0. Same thing over here, 0 and 1, you multiply it, 0 multiply 1, you get 0, right? Same thing over here, 1 multiplied by 0, you get 0. But only when you have 1 multiplied by 1, then you have a output to be 1. Okay, so that is how the AND gate, that is how the truth table for AND gate looks like. Okay, so any questions so far? So good. I'm not looking at the chat now. Did anyone of you?
So far, okay, sir.
So far, so good, sir.
Okay, so I am now monitoring the chat. If you have any question, just drop in the chat. All right, let's take a look at the last element of this AND gate, which is the timing diagram. Okay, the diagram looks kind of like the diagram for NOT gate, but it's got a few differences. Okay, the difference is over here. For a timing diagram also, you need to have the list of inputs and also the outputs. Okay, so you can draw this the other way around also. You can also draw this X like above and A and B, you can draw it below. It doesn't matter. Okay, but a good practice would be to label this like that. Okay, and output. Okay, so this, in the event that you have many input and many output, like a labeling like this would really help your people, the person who reads this to read it quicker, faster. Okay, because you get a good grouping over here. Okay, so let's talk about this. In the timing diagram, you also have this, all combinations of input over here. The first combination, let's take a look at that. So over here is 0 and A and B 0. So for this combination, the output will be 0 as well. Okay, now let's take a look at let's say A, all of a sudden it changes value. It changes value. A becomes 1, but B stays at that value. Now, what is the value like? So we know that this is just a multiplication. It's just a multiplication of 1 and 0. So like this one has this waveform. Okay, same thing over here and same thing over here. You have 0 multiply 1, you get 0. And when the two values are 1, this is where you get a value 1 at the output. All right, so that is how the timing diagram of the AND gate looks like. So, and good news is that for all other gates, that is how we, you will see the same thing again, but in a different flavor. Okay, we can do the same for the OR gate as well, like we'll see after this. Okay, so what are some very simple application of AND gate? Let's take a look at this. This is a very simple nighttime intruder detection system. Okay, so let's say you got two sensor, right? Sensor, let's say sensor, let me just use other letters so that it's not confusing. Okay, sensor, what letter am I using? Okay, let's say sensor A. Okay, sensor A and sensor B. Okay, so sensor A is a brightness detection sensor, or okay, so it can detect whether it is daytime or it is nighttime. That is the first sensor. Okay, let's call this sensor A. Okay, okay, like for sensor B, okay, let's call it heat detection sensor. Okay, obviously this name A and B, like you can use whatever name that you want. Okay, so what we have over here is, let's say this is the truth table. Okay, so this is a truth table, and we have over here sensor A and B in this truth table showing all the inputs, and then we have the output, which is the output can be alarm or any other output that you want to trigger. So let's take a look at all possible combinations over here. So if they are both 0, what does it mean? If they are both 0, it means that 0, it could be day, and 0 here, it could be no heat detection. So what we have over here is daytime, and no heat. Okay, no heat detected. Okay, because you can sense that someone is in the surrounding area by using a heat sensor, right? So if it's daytime and then there is no heat detected in the area, then you want to put the alarm to 0, no alarm. Okay, like the same thing over here. We have daytime. Yes, it's still day, and now we have 1. Okay, so we have daytime. Okay, I think the letters over here, I kind of flipped it. Okay, let's take a look at this daytime, but then there is a no heat. Sorry, let me just rewrite this again. No heat. Okay, 0 is no heat, right? So no heat detected, and day-night sensor is 1. Day and no heat. Let me see if there is a problem with this. Day, night is 1. Okay, night is 1. These are the values over here. Let me see. Night is 1. Okay. Okay, let's take a look at this. The only time that it will trigger, okay, so that I don't confuse you first, right? So the only time that you see it will trigger is when you have a nighttime, you have nighttime, and you have heat, okay, which means these two values got to be 1 over here. Okay, this is nighttime, okay, night and heat. So if you have a nighttime, so this is assuming that the intruder will come at night. Okay, so if you have a time of the day to be night and then you have a heat detected during that night, that is when you want to trigger the alarm. So all other combinations, you have daytime, and you have heat, or daytime you have no heat, you don't want the alarm to trigger. So that's why you are seeing all of this to be 0. Okay, this is an example. It's an example application. So in a real life situation, this values might change. Okay, so this sensor could come from a manufacturer, and the manufacturer will tell you this. Okay, the manufacturer will tell you this. For this specific sensor, what is the value? Okay, so one manufacturer will tell one manufacturer to the other manufacturer, it can be different. Okay, so this 1 and 0 correspond to night and day, but another manufacturer may have an opposite case. Okay, 1 and 0 could correspond to day and night. Okay, so not to worry if you don't get why is it 1 and 0 night and day. It's a specification of a sensor by the manufacturer. Okay, so this is a simple application of how AND gate can be used for a very simple, not very intelligent intruder detection system. Okay, so now let's go a little bit more quicker. So we see over here that we also have one more gate, and that is the OR gate. OR gate. Okay, so for OR gate, same thing. We have A and B as input, output if written as X. So what is difference between OR gate and AND gate is that instead of doing multiplication, an OR gate is going to add those two values. Okay, so it performs logic. Sorry, this is not multiplication. I need to correct this. This is addition. Okay, addition, and when any inputs are high. So it means that if any of these inputs this input or this input is high, then the output will just be high. Let's take a look at how this truth table will look like. So if both of the inputs, they are low, and then the output will be low. But if you have, like, take a look at the second row and third row and fourth row, if any of the input is high, then the output will just be high. So in this case, this is the input is high, the output here will be high, and if both of the input is high, the output will also be high. Okay, so then you might have questions. So A plus B, isn't A plus B like isn't 1 plus 1 equals to like 1, 0? Okay, so apparently it's not that case in logic gate, in signal. Like if you have two signals together and you add them, and in logic gates, the signal will be 1. Because why? There's no such thing as 2 in logic gates. Okay, in logic gates, it's either 0 or 1. So even though, like, you might say that, okay, 1, you have 1, and then you have 1. Shouldn't it be more than 1? Okay, in logic gates, anything more than 1 is taken as 1. Okay, so that's why we have over here, when both of this is 1, the output will be 1. Okay, the output cannot be more than 1. The maximum is 1. Okay, the minimum is 0. That's all you got. That's all the possible values in logic gates. That's why the output you get here is 1 and not 1, 0 or 2 or something else. Okay, that's a truth table. Now, same thing again, timing diagram. I'm not gonna go into details on how I draw this. I believe you already got the idea. You have the inputs, you have the outputs, and over here in the timing diagram, it should tell you all the combinations. Okay, all right, let's take a look at this one. So we have the example application, the OR gate. Okay, so the OR gate. So if you have a car, like this is something I can think of. There's other applications, there's other examples as well. This is something that I can think of. So in a car, right, you have, like, say 4 doors or 5 doors. We include the bonnet. So if any one of the doors, they're open, now what do you want to have? You want to have the lights in your cabin to turn on. So over here, let's say, for example, in this case, I don't want to put in 5 doors. I just consider 2 doors. Let's say I have a sports car, 2 doors. Okay, if any of the doors are open, I want the light to be on. If any of the doors are open, I want the light to be on. Okay, if both doors are open, I also want the light to be on. Okay, right. So again, I have said just now, this 0 or 1, it depends on your the sensor specification. Okay, some sensor has value 0 when the door is closed, but some sensor can have the opposite value. It depends from one manufacturer of the sensor to another manufacturer. Okay, so just take note of that. So this is the assumption that I make in this example. The assumption is that I have this sensor, and this sensor value is like that. It's 0 door closed, 1 door open. Okay, and based on this assumption of this value, this will be the truth table. Okay, right. Any questions so far about basic logic gates? We've covered all about basic logic gates.
Okay, so far.
Okay. I'm taking a look at my slides. Okay, right. Now, let's extend this a little bit more further. So what if you have a logic gate that's like this? So this is what gate? This is an AND gate. Okay, the shape of an AND gate. Sorry, AND gate, right? So let's say now I tell you, okay, give me the truth table for this gate. So what do you want to do? So you know that a truth table should tell you inputs. So in this case, the inputs are here, that is going inside the gate. Okay, so even though you don't see any arrow over here, the moment you see this AND gate, this flat part over here, you know that the input goes into this flat part. The output comes out at this curved part. So that's how you know the input and output. Right. So if you are going to construct a truth table for this kind of AND gate, then your truth table will have to be will have to contain the input and the output. Okay, this is how the truth table would look like. So you start by writing down the combinations, all possible combinations: 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Is there any other combinations that's available? Okay, so in a truth table, you need to cover all possible combinations. And in this case, I have covered 2, 4, 6, 8. So these are all the 8 possible combinations for the three input AND gate. Now, what about the output? How do you produce the output? So remember, for the AND gate, the output, remember the Boolean equation for AND gate just now? We have seen, let me just go back to that. For AND gate, the Boolean equation for AND gate is, okay, is this, right? It's a multiplication. All you got to do is just multiply. Okay, multiply the inputs together. In this case, you have 2 inputs, yes, but in the in the case where you have 3 inputs, you have to multiply all the 3. In the case you have 10 inputs, then you have to multiply all the 10. Okay, so let's take a look at our example here with a 3-input AND gate. Okay, so a 3-input AND gate, all you got to do is to multiply them together. So in this case, you have 0, 0, 0. So that's how you get the first row. 0 multiplied by 0 multiplied by 1. Everything multiplied together, as long as you have a 0 over here, you get a 0 as the output. Okay, 0 times 1 times 0, 0. Okay. So if you do it until the end, you will find that the only time when the output is 1 is when everything is 1 at the input. Okay, so that is how you produce a truth table for the AND gate. Of course, please produce a truth table that's more beautiful than this, okay? So that it's easier for me to read. I am writing on the tab, so I think it's not so beautiful. It's not so nice looking. If you're doing this on paper or something, like use proper lines and proper handwriting. All right, so this is what it will look like. Okay, so the output over here, sometimes it is very convenient if you write the output, the Boolean equation, or the Boolean expression at the output like that. So that is not easy to make a mistake. Same thing with a 3-input OR gate. So with a 3-input OR gate, you have this. And now the difference is that the output will be the addition of all the inputs. Okay, let's take a look at a few. So you have 0 plus 0 plus 0. The answer will be 0. It will be low. Okay, so you have 0, add with 0, and you add with a logic 1. That will produce a logic 1. Okay, remember, this is an addition. So the trick is to remember this. If any of this row has a 1, the output will be 1. Okay, so the only time the output will be 0 is when all of this is 0. Okay, so that's one way of remembering it, if you like. The other way would be to remember this Boolean expression. Okay, so Boolean expression is a very compact form to describe something. Okay, so just with this like 1-inch or 2-inch equation over here, you can express how this input, this OR gate works. Imagine you have a system with 1,000 gates. So if you have 1,000 gates, I don't think you want to make a truth table that is like has a 1,000 gates. Like it will take you forever to make it. Okay, so by knowing what is the Boolean expression, then you can accurately understand how a system works. That is the usefulness of a Boolean expression. Okay, even though some of you might not like the word expression or math. Okay, so the other example that I want to show you today is, just now we've seen that we can have 3-input AND gates, but in reality, a 3-input AND gate is just a combination of a 2-input AND gate. So how do we make these 2-input AND gates? How do we combine them? And how do we make them into 3-input AND gates? Okay, so the combination goes like this. So if you have one AND gate like this, okay, you have A, you have B, then you have X, right? So then you have A, you have B, and you have C, third input, right? So now, how do you combine multiple 2-input AND gates and form this? It's actually quite straightforward. You have A and B. So where will the third input come in? So the third input will come in if you make it like so. The third input, you can do it here. And then the output of this, channel it to this input. This will give you the same. So why do I say that these two are the same? Okay, I'm saying that this is actually this. They are the same. Why are they the same? They are the same because the truth table is the same. They are the same because the timing diagram is the same. They are the same because the expression is the same. Okay, so let's take a look at the expression. That's the shortest one. So we know that if you have a 3-input AND gate, the expression of the output would be A multiplied by B multiplied by C, right? So this is the expression of a 3-input AND gate. But what is the expression of this combination over here? Okay, let's take a look at how this works. Okay, so now we are going to do a little bit of a calculation over here. So we have this AND gate, and you have 2 inputs. So at this output over here, what is the expression? The expression at this output over here is just A multiplied by B. Okay, right. And if you do that, this A multiplied by B, this value would just go into the next gate. And the next gate also has this value coming in. So the expression at the output over here would be the first one multiplied with the second one. Would be A. This is the first one, and you multiply it again with the second one. Let's see. So take a look over here. This is the same as this. So that's why these two are equivalent. Okay, they are equivalent because they have the same expression. And if you were to make a truth table for this guy, if you were to make this truth table for this guy over here, and if you were to make the truth table for this guy over here, you would end up with exactly the same truth table and the timing diagram. Okay, right. So that is just a tip on how do you know that if two logic gates they are the same. Okay, so now a little exercise over here. So how do you produce a truth table for this combination over here? Okay, so this is a relatively simple combination, and this truth table over here, how do you get to know this truth table for this combination? Okay, so take note for this because this is the main point of today's class. All right, so I'm gonna show you how do we get the truth table first. Okay, so remember, a truth table needs to have a few things. It needs to have the inputs, and it also needs to have the output. In this case, the input is just A and B. There is no other inputs, right? Yeah. And in some cases you have more, but in this case, I'm showing you an example. There's just A and B as input, and the output will be Z or Z. Okay. So now, a truth table needs to have all the possible combinations. All the possible combinations. So for these two inputs, so what are the possible combinations? Possible combination number 1 is this, 0, 0. Possible combination number 2 is this. Possible combination number 3 is this. And this is the final possible combination. Is there any other combination that we can have? Okay, no. I believe that we have covered all this. 4 possible combination if we have 2 inputs. Now, let's take a look at the first row over here. What is the output when you have A and B to be 0? So this is where it gets interesting. We need to go to the diagram and see. So when you have A to be 0 here, 0. Okay, I'm going to draw 0. So the value of 0 goes into this NOT gate, right? The value of 0 goes into the NOT gate, and out from the NOT gate, this value of 0 becomes what? It becomes 1. Okay, remember the NOT gate just inverts everything. Okay, the NOT gate outcome from this is a 1. Okay, so the value of A, 0 here, also goes into other gates. See over here, it also goes into this gate. So it goes into this gate, 0. Okay, what about the output of this gate? The output of this gate, we don't know yet, because the output of this gate depends also on the value over here. We don't have that value yet. Okay, now we are going to see what's that value. Okay, now let's take a look at B. For B, okay, let me change my pointer color. For the value of B, let's take a look at B. B starts with 0. Okay, because we are considering the first row, right? 0, 0. So 0 as well. 0 goes into this NOT gate, and then outcome from this NOT gate is the value of 1. Okay, value of 1, and then this value of B also goes into this gate over here. Okay, now we have a complete value for this gate, and then we can compute what is the value at the output point. Okay, now let's do that. So okay, so this is an AND gate, right? So for an AND gate, it's just a multiplication. 1 multiplied with 0. 1 multiplied with 0, get a 0. Here. Same thing over here, get a 0. 1 multiplied with 0. Okay, now that we have these two values going into the last gate, which is the OR gate, so you have 0 at the output. Okay, so now we are done for the first row. Then we can write in here. When these two are 0, then we have the output to be 0. Okay, now we can do this for the rest as well. Now, real quick, let's do this for the rest. Okay, let's go faster this time. So now you have A0, B1, right? A0, B1 here. Okay, so 0 goes into NOT gate. NOT gate produces a 1. Okay, and 0 here goes into this AND gate. AND gate, right? 0 goes to AND gate, and AND gate gets here a 0. Okay, now take a look at B. B here, 1 goes into this NOT gate, and out from the NOT gate you get a 1. It becomes 0. And 1 over here also goes to the other gate. 1, okay, there's no gates in between, so you have 1, 1, 0, and 0. Now over here you have 1 and 1. So 1 multiplied by 1 is 1. 0 multiply with another 0, you get a 0. And finally, you have these two values going into this OR gate. So for OR gate, all you need to do is to add them together. So 1 and 0 plus together, you get a 1, the output. Okay, that's how you get this. Okay, so that is how we can get the output. And the same thing will apply here. And I would like everyone to take out a pen and paper and try this at home. Okay, try this at home, and hopefully you're able to get the same output as I do. All right, any problem in understanding how do we get the output of this truth table? So far, so good?
So far, okay, sir.
Okay, so I want to show you another trick here. This is also another key point of our class today. Okay, let's say, right, you have many inputs. Okay, you don't have A, B, you have A, B, C, D, E, F. Okay, can you imagine how many possible combinations this thing has? Okay, so you have many rows as a result of that. Okay, and so if I tell you that, oh, produce this truth table for every single row, then you're going to be like, are you crazy? There are so many combinations over here, and we are going to do like this, like 0, 0, and then 0, 1, and then like if this circuit is complicated, and then like it's even harder. Okay, so there's another way of doing it. There's another trick of doing it, and that other trick would be to use the Boolean equation. So So let's see how we do this using the Boolean equation. Okay, pay close attention to this, all right? All right, so let's work the Boolean equation. The Boolean equation that we want is for this Z, okay? So let's work this out from the input. So over here, we have the value of A going into this AND gate, right? Now, as we have seen earlier, this value of A coming out from the AND gate, it will be A bar because the AND gate just inverts. Okay, so that is one. Now, what about the output over here? The output over here, we cannot write it yet because we don't have the value here. Okay, now let's take a look at some other lines. So this value of A also goes into this. Okay, there's no intermediate gates or nothing. So the value of A goes into here. Okay, now we're done with A. Now let's take a look at B. The value of B goes directly into this NOT gate over here. And then out from the NOT gate, you get the value of B with a bar. Okay, same thing over here. So value of B goes into this over here, like so. Right. And now we can write the output equation for this guy. So the output for this is what? A multiplied with B. So the output here will be like this, A bar multiplied with B. Okay, and same thing over here, we have the output here to be A multiplied with B. We have a bar here. Okay, and this one goes directly into the next gate without any changes. Now, question, what is the output of Z? So Z is a result of a addition over here inside this OR gate. So we can write Z to be A bar B, which is the first one over here. And the second one is A B bar, like that. Okay, so what we have done over here is like we have a master key. So this master key can tell you the answer to all possible combinations. Okay, this master key is the output Boolean equation. Okay, so now we know that this Z over here is this, right? A bar and then B and then A B bar. So now, question. What is this? What is this value? What is the value for when 2 of this is 1? I want to know this. First choice, you can do what we did just now. We do this 1 and then we put in a 1 over here and then we do it until the end, right? And hopefully you didn't make any mistake in between. Now, the second option, which is what I'm showing you now, is a smarter choice because you already got the equation that's like having a master key. So with this master key, now we are just going to put this value into this equation and it should give you this. Okay, so if you put in that value, what do you get? Yeah, okay, let's just go through it. A and B, they're both 1. So you get 0 complement, 0 complement. Okay, I'm just inserting this here. And I have multiply with 1. And we add that with 1 multiply with 0 bar. So what do you have? So this is how you do it. 0 bar is 1. You multiply with 1 plus 1 multiply with 0 bar is 1. So what do you have? So at the end of the day, you have 1 multiply 1 is 1. Then you add that 1 multiply 1 again. What do you get? You get a 1. Okay, so you get a 1 over here. Is anyone having any trouble understanding this? Because this is a key point today.
Sir, I have a question. In the first equation line, the 0 bar, right? We are actually inserting A as 0, is it?
Yes.
So 0 bar multiplied by 1 plus, is that should be 0 or 1? Because we already assigned A to be 0, right?
Okay, so 0 bar 0 bar means what? 0 bar means 0. Bar means you invert.
Mm-hmm.
Okay.
Okay.
Okay. So 0 bar over here, meaning to say 0. A is 0, right? This is the A value. Okay. I see what you mean. Okay. I think there's a mistake over here. Thanks for raising that. I inserted the wrong value over here. Okay. Okay. Thank you for raising that up. Let me rewrite this for the sake of not making this mistake again. Okay, so when I say 0, 1 over here, sorry, when I say 1 over here, I totally inverted everything. When I say 1 over here, it means like 1 bar, not 0 bar. Okay, so B is 1. Okay, this is a multiplication. Okay, so A is 1 and B, the multiplication of 1 bar. Yes, this is what we are dealing with. Okay, so then you do the inversion. Sorry. Now 1, you invert that, it becomes a 0. Multiply 1, and then your 1 multiply with 1 inversion, you get 0. Okay, so what do you have? 0 multiplied by 1. 0 multiplied by 1 is 0. Okay, and 1 multiplied by 0. 1 multiplied by 0. Anything multiplied by 0 is 0. Okay, yeah, I think this is the correct answer. Can anyone get this together? I don't have the answer on the slides. That's why I'm doing this on the fly as we go.
I got 0 as well.
Okay, so yeah, this one is 0. Okay, thank you for raising that. If you didn't, then I might have made this mistake. Okay, so do raise questions in the class as well, because things like this happen because I don't have the answer on the slides. Okay, so you can do this for this one as an exercise and see what you get. Okay, so far, any other question based on this, what we have learned today?
No, sir.
Okay, right? So there's two ways for you to get the truth table output. One is you do this simulation. I call it simulation. And number 2 is use the equation. Okay, so simulation, like this, what we did just now. If you imagine, like you put a 1 here, you put a 1 here, what do you output? Simulation is good when you have the circuit to be simple and you like to see things like in a graphical way. Okay, but if you have a complicated circuit, you have many inputs like this, simulation might not be a good idea. Okay, so equation is a better way of doing things if you have a complicated circuit. Okay, now of course, if you like math, like you would like to see this equation more. Okay. All right, so I leave it to you. Which you can use either of these two methods. Like if you have any assignments after this. All right, so this one is the same thing. So we have over here A, B, and C. So I want you guys to do this as a homework today, and we'll discuss in the next class to see whether or not you guys get the same output as I do. Okay, I overshot my time. I was planning to finish this class, but I think we could not finish it today. It's already past 1 hour. So I think I will end this class today here. Any question?
Not yet, sir.
Okay. So as usual, this is the attendance for today, and I would like to end this class today. If you have any question like the previous quiz, feel free to stay back and I'll answer your queries.
Thank you, sir.
All right, feel free to leave if you want. You can leave now. The class is over.
Thank you, sir.
Right.
Thank you, sir.
Thank you, sir.
All right, you're welcome. All right, who was the one who asked the question in the beginning? I didn't get your name.
It's me, sir, Cairo.
Yeah, Cairo. What was your question?
Is actually regarding the last question in the quiz, the 45 plus 92.
45.
Yeah, plus 92. And I think it
Okay.
should be in the, wait, let me just double.
Let me see. Let me view the quiz here.
45 plus 92.
45 plus 92.
Yep.
Okay, one moment, please. So what do you get? Like, what was the problem with this question? I would like to see where you got stuck, and if you have a solution, can you like just share it with us and see where is the problem?
I got stuck after converting the numbers into BCD form. Yeah, BCD form, and then adding it together. So after I added it together, then I separated the parts on the left. I got 13, which is more than 9, and then on the right side I got 7, which is less than 9, and then after that I got a bit too mixed up. So I might be doing something wrong. Maybe just from the start I might be doing something wrong, but I wasn't sure. So if maybe you can just do a quick read through or pass through the solution, maybe then I could get it better, I think.
Okay, I will discuss a solution in the next class for the benefit of everyone who is not here. But I would like to understand like your solution specifically. And do you have, I believe you have your answers, right? Can you like show us what you got so that
Okay, I can should I just say it out right now?
Okay, you can, but I'm not sure if I can get you right if you say it out.
Okay, I'll take a picture and then send in the chat.
Yeah, okay, that will be good. Then I can share it here.
Okay, it's in the chat, sir.
Okay, I see I'm seeing what you have. Okay, 45 plus 92. Okay. It's a little bit small. Let me zoom in. 45 plus 92. Okay, so the problem is that okay, let me share my screen here.
I've signed mine also, but not sure whether correct or not.
Okay, 45 plus 92. Okay, let's take a look at this. Are your two answers the same? Let me check that. Okay, they look the same to me.
Looks the same, sir. Yeah.
Okay, right, then I can address them. Okay, So if you take a look at that, you separate it into two groups. How do I share this screen? Okay, I will. Okay, right, got it. Okay, I am sharing my screen now. Screen. Okay, you guys seeing my screen? This was what you sent me.
Yep.
Okay. So this was the problem, 45 and 92, right? So this on the left is 4 and then 5. Okay, nice. 1001 is 9 over here, and 0110 is 2. Okay, so these conversions are right. So okay, first and foremost, let's get the answer. What is the answer that you expect? So
137.
Oh, sorry, you did that right. So 137. Yep. Okay. So the answer that you expect is 137. Okay. So, but you didn't get 137 from what I see over here.
Okay. I did, I think, but I wasn't sure of the working wise if it's proper.
Okay. 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 So let's go through this together. So you have over here 0, 1, 0, 0, and then 0, 1, 0, 1, and then 0, 0, 1, 0, 0, 1, 0, right? So you did this addition over here, looks right to me. 1, 1, 1, 0. Okay, so there is no, this one is not more than 9, so you don't have to add 6, and there's no carry. You have to add 6. This part is correct. Okay, now let's take a look at the next portion, which is this part. Let's do that. Also 1, 0. So you 1, you have 1, right? Okay, so now we have a problem over here. What's the problem? This addition is more than 1001, right?
Yep.
Okay. So then because this is more, what you want to do is to add 6 to it.
Yeah.
So which is what you want to do is like this. You want to add 6 to this. Okay. So if you do that, like 1, 1 and 1, 1, 1, 1 is 11, 1 and 1 is okay. So at the end of the day, if you put everything, if I just carry everything down like this, so you have 0, 1, 1, 1. Okay, so what do we have? So this is the final answer. So over here, this group of 4 is 7. This group is 3. And this group, if you want to make it a 4-digit, like this is how you get it. So now I see your problem. Your problem is here, you did not add the 6. You need to add the 6 over here.
Okay, now I understand. I wasn't sure about the, I mean, I knew you had to plus the 6, but I wasn't entirely sure if I added it to the whole number as a whole, or I just added to the segment where it needed the 6, which I understand.
I see. Now I get what you mean. I totally misunderstood what you mean by talking out just now. So good thing like you send me this so that it's like it's more tailored to you, to your understanding.
Okay, thank you, sir. I understand it now.
Okay, Kumar, does that answer your question?
Yes, sir. But can you repeat a bit, sir? How you plus the 6, right? Because it's 13, so you plus 6, right? The 0, 1, 1, 0.
Correct.
Okay, so 1 plus 0, why you put a 1 on top there?
1 plus 0. Oh yeah, that's not 1. Sorry. Yep. 1 plus 0 is 1.
1, 0.
Oh, okay.
Oh,
Yeah.
okay.
1. Yeah, that makes sense. Okay, thanks. It's this. Yeah. Okay, that's a good catch. I'm so distracted with the sound around me.
But the premise is still the same, right? The 6 is only
Correct.
added to the part that needs the 6.
Correct. It's still, yeah.
So it's still the
Alright,
same.
alright.
So we divide the 1 and we put the 0, we make it 137. Correct, right? Sir?
We divide the 1. What are you saying?
Now we plus the thing, we plus it, we get 0011. So it's
Yeah.
still less than 9. And then the carry, is it? The 1 is the carry, is it?
Okay. The 1 is the carry.
The 001.
1 1. Yeah. Correct. Now this time, okay. Now this time is this time it's because you have a carry, and because you have a carry, then you have to add 6. Yeah. Correct. You're right.
Okay, so we separated it into another group of numbers. So it
Yes.
becomes
Yes.
okay.
Yes.
I got it. Okay.
Yeah. So because this one is out, right? You need to, because in BCD you have 4 digits of binary. Okay.
Oh,
So that gives you 137. Okay. Now this one is right.
because initially I did, but then I didn't know how to separate it with the one because I got 10011, so I didn't know how to separate it. I think now I got it. Really. Yeah.
Okay. That's great.
How many marks
Okay.
are you give?
How many marks? I don't know. How many marks is this?
Yeah. Okay. It's okay, sir. And maybe next time.
Thank you, sir.
Yeah, this is 4 points. Yeah. No, of course, like if you do something there's a working, like you won't get 0 unless it's totally off. Then yeah. But don't worry. You have a lot of these quizzes coming up, so just do well in your usual quiz, and you wouldn't face any problem.
Okay, sir. Sure.
Okay. Any
Okay, thank
questions?
you, sir. No, sir.
That's it, sir. Thank you.
Thank you,
All
sir.
right. Thank you.
Bye. Okay, sir. See
All
you.
right. See you.